We now start a series of videos on the concept of intermolecular interactions. The concept of intermolecular interactions follows naturally from our study of the electronic structure of individual atoms, and then from how those atoms make bonds to form molecules. Intermolecular interactions now take one molecule and a separate molecule and studies how those molecules interact with each other. Or it can also be used to study interactions between two different regions of a single molecule if the molecule is very large. Alright, so it turns out that intermolecular interactions have a key role in the life sciences. For example, if you think about how an enzyme binds a substrate, the interactions between the substrate and the enzyme are actually going to be of the intermolecular type. Generally, there's no covalent bonds being formed, only maybe hydrogen bonds, dipole interactions, and so forth. Okay, so it's those type of interactions that we're going to study in this chapter. There's going to be two things that we're going to be worrying about for each type of intermolecular interactions. One of them is what causes the intermolecular interactions. Is this a charge? Is this a dipole? Is this a polarizability? And so forth. And the other thing that we're going to be worrying about is the range of interactions. There are interactions that actually take place over a long distance in space, and there are interactions that are very short-ranged. Okay, so that would be the two things that we're going to concentrate on. Now, the first type of interaction that we talk about here is going to be the simplest one, the one that is actually the root of all interactions, and that's the ion-ion interaction. Okay, the interactions between between two fully formed ions. And it turns out that the law that captures the interaction between two ions is what we know as Coulomb's law. Okay, so again, the idea is that we're now studying ion-ion interactions. Okay, so this could, for example, be an interaction between a double helix of DNA, okay, which has negative ions, phosphates, and maybe there's a positive ion in the vicinity, say a sodium ion, okay, it's a full ion, and we're trying to understand what type of interaction do you have right there. Again, that would be a negative charge, positive charge. Okay, so this is an ion-ion interaction which can be captured by Coulomb's law. Okay, so Coulomb's law has this form. It's just the product of the charges divided over 4 pi, a constant that is called the permittivity of a vacuum, and then the distance between the charges. Right, so we can actually go ahead and then calculate the strength of this attraction between a negative ion and a positive ion. So let's assume here that the distance between these two is going to be about 30 angstrom, which is the same thing as 3 nanometers. Okay, right. So we can then plug in here all of the values. Okay, notice that if we consider 1 to be phosphate, okay, the charge of phosphate will be -1. Okay, but the actual size of the charge, okay, even though they will say that this is a -1 ion, the actual size of the charge is -1 times the charge of an electron, the elementary charge. Okay, so that will be -1 times 1.602, 10 to the -19 coulombs. Okay, the charge of the sodium ion will be +1, multiplied by the elementary charge, 1.602, 10 to the -19 coulombs. Okay, that's a constant, 4 pi. This is the permittivity of a vacuum, which is also a constant. Okay, and that will be 8.854, 10 to the -12, joules to the -1, coulomb squared, meter to the -1. And finally, this is the distance between the two ions. Okay, so notice that we have everything in SI units. That's coulomb, joules, and meter. And that forces us to place that distance there in meters. Okay, so that is 30 angstrom, 3 nanometers. This R will be 3, 10 to the -9 meters. Okay, so when you plug all those things in your calculator, you find a number that is -7.7, 10 to the -20 joules. Okay, which is a fairly small energy, as you can imagine, but that's because we're only considering the attraction of one negative charge with one positive charge. Now, things that are interesting is the order of magnitude. Okay, that's actually a moderately strong interaction, and the sign. Okay, the sign is negative, which means that this is something that is attractive. This is a stabilizing interaction. Okay, if these two ions would be separated by an infinite distance, the interaction that we calculate from here would be zero, which means no attraction. Right? But if they're interacting with each other, they're attracting with each other, that results in a negative sign in the energy, which means that the energy is dropping, the system is getting stabilized. If the ions were of the same type, both of them positive or negative, then the charge will be the potential will be positive, the energy will be positive, meaning that there's repulsion. Okay, now we can transform this into kilojoules per mole, okay, by using Avogadro's number, and this energy turns out to be about 46, 47 kilojoules per mole. Okay, so notice that that is in sharp contrast with a typical covalent bond, which is in the few hundred kilojoules per mole. For example, a CH bond in an alkane. That covalent bond energy is about 400, is over 400 kilojoules per mole. Okay, in this case, you will have that energy is about 40, in the order of 40 kilojoules per mole. Okay, so it's not as strong as a covalent bond. Okay, but it's not weak either. It's something sizable. Okay. Now, this calculation assumes that this ion and the DNA molecule, they are in a vacuum, right? There's nothing in between. But what we actually know is that if this is in a cell, okay, there's going to be water, there's going to be medium or a media in between those two ions, right? So it's not true that there's going to be a vacuum, which is what we're assuming here when we apply that expression. Instead, what happens is that, well, you might have water molecules in between. Okay, so there might be a water molecule like this, and then another one like that. Okay, and eventually you get here the ion. Okay, so the question is, how do we modify this expression, okay, to accommodate for the fact that you can have water molecules in between the two ions? Right, that is actually simply done here by modifying this expression slightly. Okay, by introducing a new parameter here that is called epsilon, okay, which is called the dielectric constant of the medium. Okay, the dielectric constant of the medium. And this is a measure for how effective the medium is as solvent molecules, how effective that is in screening the interactions between two ions, sodium plus and minus. For example, water is one of the better screening solvents between two charges. Okay, and the dielectric constant of water, okay, so this epsilon for water is about 80, okay, which is and it's dimensionless. Okay, what that means is that, well, if you're doing this in water, the calculation in water, the energy you will get, the attraction between the two ions will be about 80 times smaller than what we have right here. Okay, so water is a pretty good screening solvent. Okay. We could do this in different solvents, and what happens is that if you consider quite polar solvents, the dielectric constant is higher. If you consider apolar solvents, then the dielectric constant can be quite small. For example, hexane, which is apolar solvent, has a dielectric constant of only 2, which means that yes, that solvent can screen the interactions, the attractions between a positive and a negative ion. Okay, but it only affects it by a factor of 2. Okay, we can actually, people have been studying how you can come up with a dielectric constant that is representative of biological medium. Okay, so for example, if you're thinking about a cell membrane, we use a dielectric constant of on the order of about 3.5. Okay, which again is much smaller than water, because cell membranes usually are largely polar. The hydrophobic tails of the phospholipid bilayer is apolar for the most part. And again, that has a low dielectric constant. Okay, so this is the Coulomb's law, how it's modified if you actually have if you're not in a vacuum. And we're actually going to wrap up this section by recognizing that, well, this law works well for fully formed ions. Okay, so here you have a full +1 ion, there you have a full -1 ion. Okay, in more modern times, we're actually using this expression to calculate the interaction between partial charges. Okay, so for example, let's think about a water molecule here. Okay, let's erase this. Let's go to the vacuum again. And examine here, what does a partial charge mean? Okay, so if we take a water molecule, Alright, so we know that the oxygen atom is more electronegative than the hydrogen atoms, and that means that the electrons of this bond are more attracted to oxygen than to hydrogens. That means that there's an excess of negative charge in the oxygen atoms and an excess of positive charge in the hydrogen atoms. Okay, so that is what causes a partial charge. A way to code that is to say that, well, again, you have here a negative charge and here you have a positive charge, which are partial. Okay, there is not a full -1 and a full, or -2 and a full +1 and +1. Okay, instead you have that the partial charge will be smaller than those numbers. And we can actually calculate that for the case of water, okay, the partial charge in the hydrogen atom, in the oxygen atom is about -0.80 elementary charges, and the charge on the positive on the hydrogen atoms is about +0.4 and 0.4. Okay. Now, so it turns out that now you can use those partial charges and then plug them into this equation and start to calculate interactions between perhaps water molecules, or water molecules with solutes, or water molecules with proteins, and things like that. Okay, so it's kind of a new, more modern interpretation of Coulomb's law. Okay, but what we're going to be using the most in this chapter is just simply Coulomb's law for the attraction between two ions, in which here you will just have +1, -1, or whatever is the charge of the ion, and that is the distance between the ions. Now, something that it will be important in the following videos is to recognize that the dependence of the energy on the distance between the two charges is inverse to the R. Okay, so the power that we have right here is 1. As we move forward the next videos, we will see that for different types of interactions, you will have a change in the power of this distance, okay, that affects the range of the interaction. Here, because you have a power of 1, that means that this interaction is actually very, very long range. Two ions can attract each other over very long distances. If you start to have powers here that are larger, you will see that range of interaction starts to become shorter.